All right, good evening and welcome to our final live stream of the year. This is content review for Principles of Biology uh, 213, and today we are going over ecosystems and conservation biology. This is bringing a lot of all of them. This is bringing all of the concepts together that you've been learning over the last year and synthesizing them into some really cool exercises. So without further ado, energy transformations in a community can be diagrammatically represented as a trophic structure. Diagrammatically, make a diagram. Trophic structure is simply your arrangement of who's consuming who. All right. So diagram a simple trophic structure for a grassland community. I have already pulled in this graphic, and we can simply annotate this one. So at your bottom, you're going to have your primary producers, and this is going to be basically your plants. Let me make sure you can see that around my face. So this is going to be all of your grasses and flowers and trees and any of the other primary producers, things that are using energy from the sun to create their own biomass. These are your primary producers. Primary producers are consumed by primary consumers and decomposers. And they have a nice picture of a grasshopper or a cricket here. These are going to be lots of insects. These are going to be anything that directly eats those plants or anything that breaks down those plants. So a lot of fungi are going to fit into this primary consumer and decomposer niche, or I guess level of your trophic structure. Um, You are also going to see some numbers on this chart, which will be really handy later. And basically what this is showing is you have a 10% transfer of energy from one trophic level to the next. And so you have this dramatic decrease from 1,000 grams per that's square meter per year to 100 to 10 to 1. So from primary producers to primary consumers to secondary consumers, those that eat the bugs and the herbivores and the fungi, and then tertiary consumers. These are your apex predators. These are your eagles. These are your sharks. These are your humans, if you want to put us in this trophic structure. Um, yeah, that's a sample trophic structure or diagram. At what trophic levels do humans belong in your diagram, and explain? You could argue this a couple of different ways, but we in general have an omnivorous diet. Omnivore, us. Omni, many, vorous, to eat. We eat many things. That generally means we eat lots of plants and animals. Humans consume both uh, other animals and plants. Humans who are strictly vegetarian might eat only food derived from plants, which of course would change their uh, classification under this structure. However, if part of their plant diet is from plants and parts from animals, which are primary consumers, then humans would be classified as secondary consumers. Um, so this just kind of demonstrates some of the difficulties associated with using these very simple models. Um, so generally omnivorous, that would make us secondary consumers, with exceptions. Energy is lost at every step in the trophic structure where energy is transferred. For example, from primary producers to primary consumers. It is estimated that only 1% of the solar energy striking plants is converted to chemical energy. Only 50 to 90% of gross primary productivity, GPP, becomes net primary productivity, NPP, and only about 10% of the energy available at each trophic level transfers to the next level as biomass. Restate the preceding information in your own words and be sure to explain what GPP and NPP are and how they relate to the percentage of energy transfers from one trophic level to another. So let's start with GPP. We're mostly going to talk here. Gross primary productivity is a measure of the total amount of light energy used in photosynthesis. So GPP is total light, E for energy, used in photosynthesis per unit time. It is usually expressed in joules per square meter per year. Joules per meter squared per year. Net, so differently, net primary productivity, NPP, equals GPP minus the energy the photosynthetic organisms use for their own cellular production. E for energy of own biomass production. Whoa. So gross is all of the energy, and net is what you get when you subtract the energy required to create the organism from the gross primary production. Where does the lost energy go? And is it correct to say that energy is lost in these transfers? If not, what would be a better way of expressing this? The energy that's lost in these energy transfers is energy used by the organism for their own metabolism. Energy lost used by organism for metabolism. So for example, a primary consumer needs to eat 10 grams of plant food to gain 1 gram of biomass. So the other 9 grams of plant food are oxidized via cellular respiration to produce the ATP needed to build more biomass and to maintain the life functions of the organism. So it's not lost in the sense that it just gets emitted out into the environment. Some does, right? Like we are exothermic. We put off a lot of, or excuse me, we're endothermic, but we put off a lot of heat, and that heat is lost into the environment, and there is some heat loss into outer space that does not get recycled the back into the system. So there is some lost energy, but most of that is going into producing and maintaining our own life functions, or the organism's life functions. Measurements of photosynthetic conversion of the energy in sunlight to biomass indicate that at best, plants can convert about 75% of the energy they absorb as sunlight into biomass. The other 25% is used to support metabolism. What could account for the apparently low efficiency of photosynthesis relative to the total incoming solar energy that you calculated in part C? Did we calculate? We did not calculate the total energy. That's okay. It looks like that one was removed and the worksheet just hasn't been updated, which is fine. We can still kind of talk about the efficiency or inefficiency of photosynthesis. So since much of the Earth is covered in water, in fact, about 29% of Earth is land, of that land, only about 11% is arable, meaning suitable for agriculture. Some of the arable lands have been paved over as streets or parking lots, or covered with buildings and are not available for agriculture. In addition, most of the arable land is in the temperate region, where crops can grow only part of the year. And this alone reduces the amount of biomass produced by at least 50%. Other factors that can affect productivity include variations in weather patterns from year to year, which can produce droughts or floods that cause crop loss and therefore loss of energy stored in them. So measurements of photosynthetic, what could account for the apparent low efficiency of photosynthesis? So in a previous version of this worksheet, we were actually given um, the amount of plant biomass produced each year on planet Earth, which we can make rough approximations of using satellite imagery and things like that. And made some pretty direct calculations about the amount of solar energy in that joules per meter squared per year um, that is being turned into plants, because we can sort of approximate the amount of sunlight that we're getting as well. So again, the apparent inefficiency of this is simply due to limited surface area of Earth suitable for plants, um, seasonal changes, delta seasonal changes in productivity, and human impact in the form of construction, deforestation, consumption. If we can calculate Earth's total primary productivity, we can use it to develop an estimate of the total number of humans Earth can support. How much energy in kilocalories per year, if you're from the United States, we just call this calorie, um, would it take to support the Earth's current human population if all individuals weighed about 75 kilograms and each required 2,000 kilocalories per day? Assume 6 times 10 to the ninth humans currently inhabit Earth. Let's do some math. So we need 2,000 kcals per day per human times 365 days. Here, I'm going to actually set this up the way that my brain likes it and not just what's on the answer key here. So 2,000 kcals per day per human. Days per year equals, days cancel out, 7.3 times 10 to the fifth kcals per year per human times 6 times 10 to the ninth humans on Earth equals 4.4 times 10 to the 15 kcals per year. So our humans canceled out. Consumed by human population. That didn't work. It's fine. All right. So they threw in a couple of variables that we didn't really need to worry about, like the average mass of a human, but the average mass or the average energy consumed was important there. So how does the estimate of the energy contained in the 170 billion tons of organic material from part B in question 3 compare to the amount of energy required to support the current human population from part A in question 4? So if we accept the assumptions made in part A, the one that we just did, then we have 4.4 times 10 to the 15 kcals per year. And then yeah, because we're missing a problem here and this worksheet hasn't been updated, you guys don't have this other number that would be really important, which is 6.5 times 10 to the 17 kcals per year. And this is the amount of um, energy contained in that 170 billion tons of organic material. Um, so units cancel out. 0.68 times 10 to the negative 2. And this is a little less than 1% of the total biomass is consumed by humans. So less than 1%. Wow, that is atrocious. Consumed by humans. You have been monitoring the net primary productivity of a grassland area for several years. Over the years, NPP increased initially and then leveled off. You suspect that the availability of a nutrient is limiting productivity. Design an experiment to determine whether there is a limiting nutrient. And again, there are a lot of different answers that you could come up with here. It's worthwhile to pause and think about this for a bit. How would you test for what nutrient might be missing if one is missing? Um, so for example, you could subdivide the area into a number of smaller plots and then treat some plots by adding the nutrient and leave the others untreated. So divide into subplots and selectively add nutrient, we'll say X. Um, then measure the net primary productivity, again, produced in each type of plot. And if the nutrient is limiting, you should find higher NPPs, right? On treated plots than on untreated plots. And you can repeat this experiment with any number of different nutrients. Retest with different nutrients. So given your design, what results would you expect if only one of the nutrients you test is limiting? So if all of your test plots are each set up to test the addition of a single nutrient, you would expect to see an increase in growth only in the plot supplemented with the limiting nutrient. Because assuming all of the other nutrients are freely available in the environment, adding a surplus of them won't necessarily help. Plot with limiting nutrient supplemented will increase net primary production. Others will remain constant. What results would you expect if more than one of the nutrients are limiting? Would this affect your design in any way? Okay, I see what happened now. It's not simply that the worksheet hasn't been updated, it is that my print to PDF has eliminated entire problems, so I apologize. We're going to backtrack just a little bit because this is important. There is a question C here, and that is it reasonable to assume that all of the primary productivity on Earth is available to support humans? And if not, what else do you need to consider? So we figured that less than 1% of the plant biomass available is consumed by humans. The plant biomass in Earth ultimately supports or nourishes all of the animals, the fungi, and many of the prokaryotes. In addition, large portions of the biomass produced are not consumed, such as trees. So we can simply say plants support other organisms. Not all plants are edible. But they're all sequestering carbon very efficiently, more efficiently than any artificial process that we have yet devised. What result would you expect? So we're skipping back ahead now. What result would you expect if more than one of the nutrients are limiting? Would this affect your design in any way? If your test plots are each set up to test the addition of a single nutrient, you would likely see no difference across all plots if more than one is limiting. So if more than one is limiting, all plots will not see increased net primary productivity. And at this point, you would start testing cross combinations of nutrients or other factors. And finally, what factors other than nutrient limitation might cause net primary productivity to level off? Um, so among other things, plant growth can be limited by water availability, physical or chemical conditions related to the density of plants per unit area, the presence or absence of symbiotic mycorrhizal fungi, um, H2O, pH, other chemicals, plant density, um, presence or absence of symbionts. Testing your understanding. Two species of hawks are found at various times of the year in the United States. Hawk species A eats mice and squirrels, both of which eat seeds. Hawk species B eats snakes that feed on mice and squirrels. Given what you know about trophic structures, if other characteristics of the two hawk species are similar, which of the following are like to be true, and explain your reasoning? For a given feeding area, the number of hawk species A that could be supported is likely to be smaller than the number of hawk species B that could be supported. So remember that B eat the snakes that feed on the mice, and hawk A eats the mice. And this is not likely to be true, so we're just going to say false. Um, Species A feeding on primary consumers. Um, Primary consumers are much more likely to be plentiful, remembering that as you go higher up the trophic structure, there is less and less efficiency in transfer of energy. So you'll have an average tenfold greater food base available to hawk species A that eats those primary consumers compared to species B, which is eating a secondary consumer, which is feeding on those mice. How do I want to say that? Primary consumers, mice, more plentiful than secondary consumers, snake. Example 2, reduction in the available primary productivity in the feeding area would tend to have a lesser effect on the hawk species A than on hawk species B. Reduction in the available primary productivity in the feeding area would have less effect on hawk species A. Um, so again, we're kind of looking at the relationship or the proximity to those primary producers. This is not likely to be true. Assume primary productivity is reduced from 100 kilograms of biomass to 50. So we cut it in half. Prior to the loss, the feeding area would support 10 kilograms of primary consumers. 10% of 100 is 10. That 10 kilograms would be used to support 1 kilogram of secondary consumers, snakes and hawk A. Right? This is our primary producer. This is our primary consumer, which is mice. And then we have secondary consumer is hawk A and snake. And then you have tertiary consumer. This is hawk B. So if we cut our foundation in half, is going to have a far greater impact on um, organisms closer to that primary production. The percent reduction for both populations would be about the same. Yeah, I'm sorry. I have to amend what I just said because it's not that it's going to affect those organisms closer to primary production necessarily. It's going to impact them all proportionally. So if primary production is reduced by 50%, then primary consumers, their available energy is also reduced by 50% on up the chain. All right. If the seeds consumed by the mice and squirrels in this feeding area were contaminated with heavy metals, you would expect to find much lower concentrations of heavy metals in hawk species A than in hawk species B. So first you have to know that heavy metals show up, remain in the trophic structure from top to bottom. So a relatively small concentration of heavy metals in primary producers, these seeds, is going to stay all the way up that food chain in the same concentration without reduction. So this is actually likely to be true. Um, you'll find much lower concentrations of heavy metals in hawk species A than in hawk species B. Hawk A would need to eat 10 grams of mice and squirrels for every gram of hawk mass added, and hawk B would have to eat 10 grams of snake that ate 100 grams of mice and squirrels for every gram of hawk mass added. And as a result, heavy metals which are not metabolized but accumulate through the food chain would be found in much higher concentrations in hawk species B. So hawk species B consumes indirectly a much greater biomass, which leads to high concentration of heavy metals. What factors can affect the survival of species or community? I'm going to read this off my other screen because it's not appearing here. Making decisions to preserve communities requires an understanding and integration of many factors. Assume you work for the US government and manage a large national forest. You are told that to maintain the economy in the area, the government has agreed to allow foresters to remove 500,000 acres of trees from a 1,000,000 acre parcel. This parcel is almost square. It's going to simplify our math. You have asked your staff to do an analysis of two possible methods for implementing the plan. Proposal one, you split the 1,000,000 acres into two parcels of 500,000 acres each and allow the foresters to harvest all trees on one of these parcels. Divide it in half, deforest one half. Proposal 2, divide the million-acre tract into 50 parcels of 10,000 acres each and allow the foresters to cut half the trees in each parcel. So we have a bunch of parcels, or excuse me, that's not how we're dividing it. We're dividing it into many parcels and then dividing each of those parcels in half to deforest it. Perhaps like so. And I'm not going to do the rest of that. List some of the ecological advantages and disadvantages of each proposal. Uh, Please note that each proposal has many possible advantages and disadvantages, and the following are just a few of these. Okay. So, proposal 1, we take the entire, I should mark these. This is proposal 1, this is proposal 2. So some advantages of proposal 1 is infrastructure. Fewer roads are going to be needed. So fewer roads means there's going to be less intrusion into the rest of the forest. There's going to be less material and labor and time needed to access that forest. It's going to be less disruptive to the surrounding forest that is left untouched. Right? So there's going to be less edge habitat uh, relative to interior habitat, less edge habitat relative to uh, interior habitat. Let's do stars. Interior species may be favored more in this case. So those that are living in the deep part of this forest are probably going to be fine because they will be unmolested by the deforestation happening next to them. And finally, harvesting and replanting would be more focused and therefore could occur more efficiently with less disturbance to the other 500,000 acres. So harvest and replant, more focused and efficient. So the big advantages are that, what was it, 500,000 acres um, remains largely unmolested. It's going to mean stay pretty much the same way that it was, perhaps with some caveats. So disadvantages. Let's do the regeneration trees. The regeneration rate for trees would be slower because seed sources are more distant. Um, you're also going to have more soil nutrients lost from the land because you're basically clear cutting it. There's going to be a lot more runoff. There's not going to be those dense root systems and also that protection from the weather that would normally be there to slow rainfall and things like that. So you're going to have soil nutrients, increased soil nutrient loss from land. And finally, you're going to have complete loss of some communities that could result in if animal or plant communities were disturbed heterogeneously, that is in many ways. So you would be reducing a lot of that, the local communities you could be eliminating them entirely. Complete loss of some communities. If you have a rare species of bird that only lives in that spot, gone forever. All right, advantages of proposal two. So this is the one where we're subdividing it into many parcels and then only harvesting half of each parcel. Um, this is going to have a much more distributed impact, right? So all cut areas would be closer to seed sources, and natural regeneration would be a lot faster. Fast, natural regeneration. Fewer soil nutrients will be lost due to runoff. You're keeping those root systems intact. You're maintaining the cover that is protecting that soil. You have a lot more plant biomass that is able to absorb water and weather and wind uh, and traffic. Disturbed animal species may be able to just move to an adjacent uncut area. So in example one, maybe these rare birds live all over that clear-cut area of the forest, but only the ones closest to the border with the uncut forest are able to migrate over, and only those ones persist. You're going to have a much smaller proportion of species that persist relative to whatever biodiversity was living in that entire area. So the smaller parcels and subdividing those, um, thank you, helps a lot to preserve those species. And finally, species that roam over a wide geographic range may benefit. So we're basically decreasing the density of the forest overall, right? And this is going to open lanes throughout the entire million acres. And so those animals that rely on migratory pathways or that have a broad range, like grizzly bears, like mountain lions, um, will be able to move around a lot easier following this clear cut. And so it's going to present some advantages to certain species. Disadvantages. There's going to be a lot more roads. You need roads to access these areas. You need roads to um, haul the lumber out. And so you're going to end up with more edge and more disturbance. It's also going to increase the amount of time that logging operations are going on because it's logistically a lot more difficult. Um, Increased resources, all of that. The result may be invasion of more exotic species. So we talked about those animals with having a wide range and opening these lanes for them to move around more easily. That can also work to their detriment by making it easier for species out that would normally not be able to move around in this area to get in. They could also hitchhike on the logging operations. So if you've got trucks, there's a specific example. Um, this was an aquatic example, but in Colorado, uh, a specific species of, I think it was the zebra mollusk, zebra clam. Oh man, I'm gonna have to look that up now. But boaters basically bringing in these exotic um, shellfish that decimated local populations, and just from hitching a ride on machinery moving back and forth, creating new lanes. And finally, replanting efforts would be more diffuse and less efficient. So replanting less efficient. And depending on what we're talking about, if this is a plant that can reseed itself pretty easily, um, doing this subdivided, the proposal two might not, you might not need replanting operations anyway, because the sources of seed plants are close enough that they can regulate themselves and replenish themselves. So lots to think about. Um, it's never a one size fits all kind of solution. Given the characteristics of the various animal species described below, which of the forest cutting proposals would be more likely to ensure continued success of each animal species? So now we're getting even more granular here. Explain your answers. C, Arnivora. Uh, Carnivora is a secondary and occasionally a tertiary consumer or carnivore. Behaviorally, it roams over about 20 square miles of home range in search of food, for example, rabbits and foxes. All right, I'm sorry, we got to do some math. So 1 square mile is 2.8 times 10 to the 7 square feet. So 20 square miles is 56 times 10 to the 7 square feet. Oh, that's why I'm doing it this way. Sorry. They write it out as a word problem, and I strongly dislike that, but that's fine. Per 1 mile squared. 1 acre is 2.6 times 10 to the 5th square feet. Why are we doing it this way? Oh, separate problem. Why are we doing it this way? 1 acre equals 2.6 times 10 to the 5th square feet. Okay, so 1 million acres. It's 26 times 10 to the 10 square feet, or 26 times 10 to the 10 divided by 2.8 times 10 to the 7, or about 9.3 times 10 to the 3 square miles. Okay, so this area could support as many as, so this is the number of square miles we have. Each of these individuals roams over 20 square miles of home range. So that gives us 4.6 times 10 to the 2 carnivora, if these were the only carnivores. So half of the forest in proposal 1 contains 4.6 times 10 to the 3rd square miles. This area could support a maximum of 2.3 times 10 to the 2 carnivora. So 4.6 times 10 to the 3rd miles squared. Just keep that bit. So half the forest in Proposal 1 contains 4.6 times 10 to the 30 square miles. This area could support a maximum of 2.3 times 10 to the 2 carnivora. The half of the forest left in Proposal 2 is patchy. And although patches would be contiguous, the patchiness of the environment may have an effect on its desirability to predators, but also on the size of the existing population, the minimum number of individuals required to maintain the population long term, the response of the carnivore to disturbance, and other factors. So the answer here is it's going to depend. That was a very mathematical way of saying it's going to depend. All right. Rodentia is a small rodent-like herbivore that exists in small numbers in the forest. Its preferred food and habitat are found along the edges of the forest and are composed primarily of herbaceous, non-woody annual plants that produce tender shoots in the spring and plentiful seeds later in the year. The key word here is edges of the forest. Proposal 2 created a lot of new edge forest. So Proposal 2 will benefit this animal a lot more. Um, simply because it produces more edge habitat. If the success of this species is directly related to the amount of edge habitat, then it would be more successful if Proposal 2 were adopted. Because increased edge habitat. And it's cut off, but I can read off of the other form. Predatoria is a predatory bird that feeds on small rodents and occasionally on snakes and other reptiles. It can range over large distances looking for food. It nests in hollows that occur naturally in a particular species of tree. These hollows are not found in trees under 20 years of age, but are commonly found in trees 40 years and older. So this is old growth forest. If we assume that 40-year-old trees are randomly distributed throughout the forest, then both proposals would eliminate half of these trees. But, in other words, both proposals would reduce the available nesting sites for the species by half. The immediate effect on the population would depend on the existing population size. If the numbers of predatoria in the population and the number of available nest sites are currently about equal, then half of the predatoria would lose their nest sites. They would not be able to reproduce and would eventually die without leaving offspring. If the predatoria population is much smaller than the number of available nesting sites, then there may be little immediate effect on the population. But if this plan is repeated in 20 years and the other half of the forest is cut, then the predatoria species would have no nesting sites left and would disappear in this region. So this one isn't really a plan one or plan two. This is a long-term planning problem where you have to make sure that some old growth trees are left intact somewhere in the forest, um, enough to support this population of predatoria. Conservation biologists have debated extensively which is better, many small reserves or a few large ones. What factors should be considered in making judgments about size and location of reserves? What is better will vary from species to species, of course. It's kind of a theme in these classes. Some species roam over wide ranges and may do better if many small reserves are connected into one large one. But some species can survive in only old growth forest areas that have appropriate nesting sites. So range, habitat suitability. Other species are much more successful in open areas or edge habitat. In other words, the requirements of the species to be preserved should be of primary importance in making decisions about the size and location uh, of reserves. So reserves being places that won't be cut, places that will be protected no matter where they are in this plan. Some ecologists argue that we should be concerned about preserving the largest number of species, so in other words, maintaining biodiversity. Others argue that we should be most concerned with saving those species judged to be of unusual importance. Develop an argument to support one of these viewpoints. Your argument should be based on our existing understanding of biology in general and ecology in particular. Plenty of logical arguments could be proposed here. Um, in developing your argument, you should really consider the habitat and energy or food requirements of the plant and animal species, as well as any behavioral requirements of the species. So, in my home states, where I grew up, Colorado and Wyoming, grizzly bears were a hot, hot topic for much of my childhood. Um, Plenty of folks did not want them reintroduced to Yellowstone National Park and the surrounding area, um, or didn't want any efforts to increase their numbers because they supposedly pose problems um, for farmers and ranchers. And um, this was also true for especially for wolves in Yellowstone National Park. And what they found was once they did reintroduce the wolves, they kept the number of deer, they kept the deer and elk population in check so that primary producers, plant species, could bounce back, and they reshaped the river systems in the area and allowed them to sequester a lot more carbon and um, slowed down the water flow. So a lot more of it stayed in the ecosystem, and the whole ecosystem from top to bottom bounced back. So the wolves were really a keystone species in that area. That may actually be an example we've talked about in another live stream. I seem to remember that. Um, the grizzly bear one came to mind because if you are looking at a conservation plan, talking about deforestation, um, that is going to, say protect the grizzly bear's range, but you're going to cut off all of their food supply from what they need, then you may as well be, um, then you're impacting the grizzly bear population and undercutting your own goals of preserving them if that is your stated goal, right? So think through these things. Um, if you keep the forest intact to protect the bears, but then you build a dam and the salmon that they rely on to survive the winter can't get there, you've killed all the bears. Based on your answers to the previous questions, which of the proposals for removing 500,000 acres from the national forest in question would you recommend, and explain your reasoning? Again, lots of possible arguments can be developed to support either proposal one or two. Your argument should include a comparison of the advantages and disadvantages of each proposal as they relate to both the plant and animal communities in the forest. So think about these things. I can't hand you an answer necessarily, um, but I will be reading these. Uh, so don't forget to turn in your worksheet. for that sweet, sweet extra credit. And spoiler alert, I skim most of these just to make sure that you've put something, but I will be reading these ones. And yeah, if you really want a discussion about these, email it to me. Don't just submit it to the worksheet form. Email it to me and we can talk about it. I have a little bandwidth this week, even though all of the exams are coming up. So thank you all so much for your time and attention this year. This may very well be my last live stream for Principles of Biology. My future at PSU is uncertain because I have finished my studies here, or I will have in 2 weeks. So it has been a pleasure. Thank you all. I hope to see you all in the future in our professional lives. Good luck with your studies. I will see you again soon.